Okay, now it's time for homework number 7. Let's see if we can do some of these problems before it gets darker than this. Focus on concept question 10. As the text discusses, the conservation of linear momentum is applicable only when the system of objects is an isolated system. So an isolated system is a system where neither matter or energy flows in or out, if you talk about thermodynamic systems. But in general physical systems, an isolated system is the one that has no effect from any other system, it's just by itself. So a ball is dropped from the top of a building. The system is the ball. So does it have any other thing affecting it? Yes, we're going to have air resistance and the rest. So it says a ball is dropped from the top of a building. The system is the ball and the earth. Okay, now that makes sense. So that's an isolated system. Then a moving billiard ball collides with a stationary billiard ball on a frictionless pool table. It's not isolated, so the moving ball also has other things that can affect it. Then a car slides to a halt in an emergency. The system is the car. We have other things going on in the car that can affect the car. A space probe is moving in deep space where gravitational and other. So that is an isolated system. So it's a little kind of confusing. But you're going to see the correct answer is 2 and 5 because those are the systems you can easily isolate. So if a ball is falling, you cannot isolate the earth from the ball because the ball is falling under gravity, you understand? So the ball and the earth becomes the isolated system. So 2 and 5 are the isolated systems, and that's C, okay, for that part. So in a science fiction novel, chapter 7, problem 16, two enemies, Bonzo and Ender, are fighting in outer space from stationary positions. They push against each other. Bonzo flies off with a velocity of plus 1.2 meters per second, while Ender recoils with a velocity of 4.3 meters per second. Determine the ratio m Bonzo over m Ender. So we're going to have mass of Bonzo over initial velocity of Bonzo plus mass of Ender over initial velocity of Ender equals mass of Bonzo, final velocity of Bonzo, mass of Ender, final velocity of Ender. So this is the conservation of momentum for both. So initially they were at rest, so they have 0 initial velocities. So 0 plus 0 equals, then after they push each other, so we want mass of Bonzo over mass of Ender. So let's just do this before. V final Bonzo plus mass of Ender, V final Ender. So we have mass of Bonzo over mass of Ender will be, mass of Bonzo over mass of Ender will be, okay, let's do this first. Negative mass of Ender, V final of Ender equals mass of Bonzo, V final of Bonzo. So mass of Bonzo over mass of Ender will be negative V final Ender over V final Bonzo. Okay? So what we are told that, keep moving this cable around, sorry guys. So we are told that velocity of Bonzo is plus 1.2 and velocity of Ender is negative 4.3. So this negative 4.3, so there's minus in the equation first divided by 1.2. So if I do 4.3 divided by 1.2, that'll give me 3.583. 3.583. That becomes the ratio of their masses, okay? Becomes the ratio of their masses. So let me confirm that. 4.3 divided by 1.2. Yep, 3.58. Good. So let's go to the next problem. Chapter 7, problem 19, just down there. It says that a lumberjack of Mazda is standing at rest on one end of a floating log of Mazda that is also at rest. The lumberjack runs to the other end of the log, attaining the velocity of that relative to the shore, and then hops onto an identical floating log that is initially at rest. So to solve this problem, it's better to have a picture of what's going on. So whoever this guy is, lumber somebody, so he's there's another log here. So he's gonna hump from here and jump onto this guy, okay? Like that. So when he jumps, he has some velocity. Is that okay? So he attains a velocity of 3.25 meters per second before jumping. So momentum here is conserved of the system. So total initial momentum before is equal to total final momentum. So here we're going to have mass of lumberjack, initial velocity of lumberjack, plus mass of, so what is this saying? Log, initial velocity of, the log and lumberjack both start from L. So I'm going to say, floating log. So I'm going to say F. Okay, initial velocity of floating log equals mass of lumberjack, final velocity of lumberjack, plus mass of floating log, final velocity of floating log. Okay? Okay. So these are both 0 initially, but as it takes off with a final velocity, then let's see what happens. So initially, the momentum is 0 for both the lumberjack and the floating log. Then here we'll have mass of log, final velocity of lumberjack, plus mass of floating log, final velocity of floating log. So negative mass of lumberjack, final velocity of lumberjack equals mass of floating log, final velocity of floating log. So they're asking us to get the final velocity of the floating log. So the final velocity of the floating log will be negative mass of lumberjack, velocity of final of lumberjack divided by mass of floating log. So mass of lumberjack is given to be 110 kilograms. And we know the final velocity with which it took off, 3.25 meters per second, divided by mass of the floating log, 205. So there's a minus there. So the minus sign is going to give us minus 1.74 meters per second. So the negative tells you it's like a recoil velocity for the log. So the lumberjack pushes on it and jumps. The log moves in the opposite direction of the lumberjack with that magnitude. Okay, so the second one says determine the velocity of the second log as he lands on it. Is that okay? So as he lands on it, he comes to rest. Is that okay? So now he's coming with some initial velocity. So let's come here. Where is it here? Okay, good. So let's go to the B part. So he's coming with some initial velocity, which is the 3.25. So mass of lumberjack times 3.25. So this one was at rest before, plus 0 equals the final momentum is mass of lumberjack, final velocity of lumberjack. We're told he comes to rest. Then mass of floating log, this second one, final velocity of floating log. So he comes at rest, lumberjack comes at rest on the second floating log. So this is 0. The floating log was initially at rest, so this initial momentum, he was coming with this speed initially from this guy. Then final momentum, he comes to rest, but this guy, where is it called? This guy moves with some speed. So, but the thing is, if he's coming to rest on that guy and this guy moves with some speed, then definitely he's going to have the same speed as that guy as it moves. So even if he comes to rest, is that okay? As he says, comes to rest relative to the second log. Is that okay? So relative to the second log, he comes to rest. But we want his velocity of the second log relative to the shore. So relative to the second log, he comes to rest. But relative to the shore, he has some velocity. So we're going to ignore. But this velocity and the final velocity of the log will be the same. So mass of lumberjack, V, plus mass of floating log, V. They have the same velocity after he lands on it. Okay? So we need to find that velocity of the second log, which is this V. So mass of lumberjack plus mass of floating log, V. We are finding V. So V becomes mass of lumberjack times 3.25 divided by mass of lumberjack plus mass of floating log. Okay? So that becomes 110 times 3.25 all over 110 plus 205. Okay? 110 plus 205. So let's do that and see if we get 1.13 meters per second. So let's do that calculation. Let's hope this is still clear for you guys to see. So 110 times 3.25 divided by 110 plus 205. That's 315. Yes, 1.13 meters per second. So that's the correct answer. 1.13 meters per second. Good. So that solves the second problem. So let's go to the next problem. It says the lead female character in the movie Diamonds Are Forever is standing at the edge of an offshore oil rig. As she fires a gun, she is driven back over the edge and into the sea. Suppose the mass of the bullet is that, and its velocity is that. Her mass, including the gun, is that. What is the recoil velocity? So, before shooting, initial momentum is 0 for both gun and her and the bullet. After shooting, the bullet goes this way, then the recoil of the bullet moves her the other way. So all we're going to have for this problem is total final momentum. Total initial momentum is 0. So we're going to have 0 equals total final momentum, mass of bullet, final velocity of bullet, plus mass of girl, final velocity of girl. Okay, so we are asked to find mass of the final velocity of girl, her recoil velocity. So final velocity of girl plus the gun together equals mass of bullet, final velocity of bullet, with a minus sign divided by mass of girl. So this comes a minus sign and divide by mass of girl. So what is the mass of girl plus gun together? 53 kilograms. 53 is under. Mass of bullet 0.033. 0.033 times velocity of bullet 709. Okay, so that's it. So we're going to get a minus answer because the girl and the gun will move in the opposite direction of the bullet, which was positive 709. So let's do 709 times 0.033. 709 times 0.033 divided by 53. 0.44. So do we have that? Negative 0.4, of course, so because we have minus here. 44 meters per second. Correct. Now the next question says, under the same assumption, what would be her recoil velocity if instead she shoots a blank cartridge? So she's not shooting the whole bullet, just a blank. So the same formula, minus mass of bullet, now 5 times 10 to the power minus 4 for the cartridge, with the same velocity 709 over the mass of the lady plus the gun, 53. So we just change that. I'm going to get the answer there, negative 0.007 meters per second. Just the same thing as the answer you have there. Okay? Yeah, so that solves the problem for that. So we'll go to the next problem, chapter 7, problem 26. Adolf and Ed are wearing harnesses and are hanging at rest from the ceiling by means of ropes attached to them. Face to face, they push off against one another, so the initial velocity is 0. Adolf has a mass that, and Ed has a mass that. Following the push, Adolf swings upward to a height of this above his starting point. So to what height above his starting point does Ed rise? Okay. Okay. So we can, this is a kinetic energy problem. So let's see what we can do from here. So we're going to convert the energy they push, the kinetic energy they gain from pushing each other to, they lose that kinetic energy and gain potential energy to rise to some height. Okay. So when they push off each other, I'm going to have minus mass of Ed. Let me see, Adolf and Ed. Final velocity of Ed, let me say plus mass of Adolf, final velocity of Adolf equals 0, initial momentum 0. So this is your final momentum. So I know that Adolf has a mass of that and Ed has a mass of that. Adolf swing to that height. So let me find final velocity of Adolf. Final velocity of Adolf is mass of Ed, V final Ed over mass of Adolf. Is that okay? So now I can get this final velocity of Adolf from that height, that mgh equals half mv squared, assuming the initials are 0. So m cancel m. So here I'm looking for V final Adolf. The kinetic energy of Adolf is converted to mgh. So V final Adolf is 2gh squared. So that would be 2 times 9.8 times the height he reached, which was 0.74, square root of that. So let me do that. Let me do that really quick and see what I get. Make sure you guys can still see the board. 2 times 9.8 times 0.74 is that, square root of that. 3.81. So this 3.81 meters per second. Okay, good. Swings upward to ahead of that. So to what height above his own starting point does edge rise? So now let's put this speed here for V Adolf, and then find V final of Ed. Is that okay? Don't forget there's a negative sign here. So V final of Ed will be negative mass of adult, V final of adult, divided by mass of Ed. So we just got V final of adult. That's the same thing, which is 3.81. We put it here. So V final of Ed is negative mass of adult. So we're giving mass of adult to be 100 times V final of adult 3.81 over mass of Ed 72. So 381 divided by 72, what does that give us? 5.29. Negative 5.29 meters per second. So what height will this speed give us? So we have to put it in descent speed. mgh for Ed now, this was for Adolf, equals half mv squared. So the height will be half mv squared divided by g. We'll find h here, m's cancel, so it's half v squared divided by g. So I'll do that right here. So h for Ed will be half v squared over g for Ed. So we just got the v final of Ed to be 5.29. Negative, when we square it, it becomes positive squared. So let's square 5.29. 28. So this is 5.29 squared. You can put minus there, it doesn't matter, over 2 times 9.8. Okay, so 28 divided by 2 divided by 9.8, 1.43 meters. 1.43 meters. So that gives me the height to which he can go after getting his speed and converting his kinetic energy to potential energy. Okay? Okay, good. Let's go to the next problem. We're almost done. Here. So we have 3 more problems to go that are right here. Chapter 7, problem 29. A 2.19 gram bullet traveling at a speed of 448 meters per second strikes the wooden block of a ballistic pendulum, such as that in figure that. So we did this in our recitation last time. The block has a mass of that. Find the speed of the bullet and block combination immediately after collision. How high does the combination rise above its initial position? Okay. I'll have to look for that figure, but let's see if we can. If we have everything, we need to solve this problem first. We don't have to look for anything else. So let's try to solve the problem. We've done this before in the recitation, so it's supposed to be a lot easier. It's getting darker and darker before you guys can't see nothing anymore, and you can't even see me. Okay. So we know ballistic pendulum is like this. It hangs on a rope, and then the bullet strikes it, and the bullet moves it to a height h. Is that okay? So it goes to a height h. Okay. So this is L minus h from here to here, and this is L, and this is theta, and the bullet comes with an initial speed here. So from these we know only the bullet has initial momentum. Mass of bullet, V initial of bullet equals mass of bullet plus mass of block with a V final. So this is the total final momentum. Initial momentum is only bullet, the block was not moving, so we don't have that. So it should be plus 0 for the block. But they both move with the same velocity after. Then after the move, half mb plus m block V squared equals mb plus m block gh. So this is the energy. So these are the 2 equations we need. The momentum equation, and after the momentum is completed, after the strike, the kinetic energy gain converted to potential energy. So it loses itself to potential energy to height h. So that's all we need. So let's see what the problem says. The speed of the bullet combination after. So we're looking for V. So we are given mass of the bullet and initial velocity of the bullet and mass of the block. So we can find V. So V from this guy, V is just mass of bullet, initial velocity of bullet over mass of bullet plus mass of block. So that's easy. So mass of bullet is 2.19 grams, so 0.00219 kilograms divided by 1000 times the initial velocity of bullet 448 divided by mass of bullet plus mass of block 251 grams, 0.251 plus 0.00219. So we do this, and if you do that carefully, you're going to get the answer there to be 3.88 meters per second. 3.88 meters per second. So sum this together, then multiply this divided by those. Now after getting that speed, the next one is to find the speed of the height. So we're looking for h. So now this is v. We put v here. These masses cancel. So h is v squared over 2g. So square this divided by 2g. That will give you h. So h is v squared over 2g immediately, because these masses will cancel. So we got v from the first equation. We are getting h from the second equation. Is that okay? The mass combination of the bullet and block cancel. So I have v squared over 2 equals gh. So h is v squared over 2g. Okay, so square 3.88 divided by 2 times 9.8 under, you're going to get the second answer there to be 0.77 meters. And that solves the problem. Before it gets darker than this, let me make sure you guys can still see at all. Okay, making sense. The next problem, Batman has that mass. That's problem 31, chapter 7. Jump straight down from a bridge into a boat with that mass, in which a criminal is fleeing. The velocity of the boat is initially that. What is the velocity of the boat after Batman lands in it? So simple. So only the boat has some initial velocity. Is that okay? So when Batman lands in it, then Batman changes the velocity of the boat. So let's do that. So it's going to have the change in momentum like this. So because Batman is jumping straight down, he's jumping into the boat, so he has vertical velocity, doesn't have horizontal velocity. So his momentum cannot affect the momentum of the system. So all we're going to do here is simple. So the initial momentum is only for the boat. So mass of boat, initial velocity of boat, plus 0 for Batman because he's moving perpendicularly, equals mass of boat plus mass of Batman times the final velocity. They go together, okay? So mass of boat is given 553 times initial velocity of boat 12 equals mass of boat 553 plus mass of Batman 85.3 times v. So we find v, the common velocity after. So v is just 553 times 12 over 553 plus 85.3. If you do that carefully, you just get 10.4 meters per second. That's easy as taking a phantom. Very easy. And then the last one is, let me make sure it's 10.4. Just I've been ignoring some calculations just to make sure you guys don't get stuck. I'm just trying to make sure. So 553 times 12 divided by 553 bracket plus 85.3. Yeah, 10.4 meters per second. So I'm correct. So let's do the last one. Chapter 7, problem 32. A car of that mass, 1040 kg, is traveling at that speed. When it collides head-on with a sport utility vehicle, so they move in opposite direction with that mass. We don't have the velocity of the other guy, but they both come to a halt. So in the collision, the two vehicles come to a halt, so they stop. So nothing after collision. So momentum after collision is 0, but they have momentum before. So mass of car, initial velocity of car, with the sport utility vehicle, mass of sport utility, initial velocity of sport utility equals 0 for final, because they come to a halt. So we are looking for the speed of the sport utility. So V initial of sport utility before they collided is mass of car, V initial of car, divided by mass of sport utility. So mass of car, 1040, initial velocity of car, 28.4, mass of sport utility, 2440. So this is going to be minus. So this will give us the velocity. That's why it's minus, because it has to move in opposite direction to have a head-on collision. But they are looking for the speed, so they just want the magnitude of that. They don't need the direction, actually. So if you do 1040 times 28.4 divided by 2440, you're just going to get negative 12.1 meters per second. So the minus sign tells you it's in the opposite direction of the car, but the speed is the magnitude. So 12.1 meters per second is the answer for the speed, not the negative answer. Okay. So the momentum problems are usually easy. Just know the conservation. The problem is to understand what happens initially, what happens after the collision or explosion or whatever interaction you have before or after that interaction. Okay, thank you guys. Before it gets darker than this, I'm going to see you guys for homework number 8 next. Have a good one.